On November 5th, 2018, at a distance of approximately 11 billion miles from Earth, something happened that changed the history of human exploration permanently and quietly, and without a single headline that matched the weight of the moment. A spacecraft launched in 1977, running on a power supply that had been declining for 41 years, carrying instruments designed before the personal computer existed, crossed a boundary that no model built on Earth had ever been able to directly verify. It left the solar system. It entered interstellar space. And because this particular spacecraft was carrying a working instrument that its twin had lost 38 years earlier, what it recorded at that boundary and in the days and weeks that followed produced 5 peer-reviewed scientific papers published simultaneously in Nature Astronomy that collectively described a crossing unlike anything the models had predicted. The scientists who received the data used careful, measured language, as scientists always do. But beneath that language, in the specific numbers and the specific anomalies and the specific ways in which the data refused to match the predictions, was something that the project scientist for the Voyager mission summarized in a single sentence that said more than any technical description could. Without this new data from Voyager 2, he said, we would not know if what we were seeing with Voyager 1 was characteristic of the entire heliosphere or specific just to the location and time when it crossed. What Voyager 2 found when it crossed the edge of our solar system confirmed that the anomalies were real, and it found new ones that nobody had been looking for. The Voyager program was conceived in the late 1960s, when astronomers recognized a rare alignment of the outer planets that would not repeat for approximately 175 years. Jupiter, Saturn, Uranus, and Neptune were drifting into positions that would allow a spacecraft to use each planet's gravity as a slingshot, gaining speed and redirecting course for the next target without burning additional fuel. The 2 Voyager spacecraft, launched 16 days apart in the summer of 1977, assigned different trajectories for different scientific objectives. Voyager 1 took the faster path, reaching Jupiter in 1979 and Saturn in 1980, before being flung upward out of the plane of the solar system on a trajectory toward interstellar space. Voyager 2 took the longer route, swinging past Jupiter in 1979, Saturn in 1981, then making the only close flybys of Uranus in 1986 and Neptune in 1989 that any spacecraft has ever conducted, before being directed southward and outward on its own path toward the boundary of the solar system. The difference in their trajectories meant that when Voyager 1 crossed the heliopause in August 2012 at a distance of 121.6 astronomical units from the Sun, Voyager 2 was still years away from the same boundary, traveling in a completely different direction, at a different angle relative to the Sun's equator, in a different part of the vast bubble of solar influence that encloses the entire planetary system. The heliosphere is not a perfect sphere. It is shaped by the pressure of the interstellar medium flowing past it, as the solar system moves through the galaxy, compressed on the side facing the direction of travel, and extended into a long tail on the opposite side. Voyager 1 crossed the boundary in the northern hemisphere of the heliosphere at a heliolatitude of approximately 35 degrees north. Voyager 2 crossed it in the southern hemisphere at approximately 31 degrees south. 2 completely different locations, 2 completely different sets of conditions, and yet the distance at which they crossed was almost identical. Voyager 2 traversed the heliopause when the probe was 119 astronomical units from the Sun. Voyager 1 made the crossing at nearly the same distance, 121.6 astronomical units. This consistency is very strange, in the sense that one crossing occurred at the solar minimum when the solar activity is the least, and the other one occurred at the solar maximum. Solar maximum and solar minimum represent the 2 extremes of the Sun's 11-year activity cycle, when the intensity of the solar wind, the continuous stream of charged particles blown outward from the Sun, reaches its highest and lowest levels respectively. The solar wind is what inflates the heliosphere. When the solar wind is more intense, at solar maximum, the heliosphere should expand outward. When the solar wind is less intense, at solar minimum, the heliosphere should contract inward. Voyager 1 crossed at solar maximum when the boundary should have been pushed outward. Voyager 2 crossed at solar minimum when the boundary should have been pulled inward. The boundary should have been at different distances for the 2 crossings. It was at almost exactly the same distance for both. Something about the structure of the heliopause in those 2 regions, separated by 62 degrees of heliolatitude and 6 years of solar cycle, produced almost identical crossing distances under opposite solar conditions. The explanation for that consistency is not fully resolved in the current models of heliospheric structure. The most compelling evidence of Voyager 2's crossing came from the instrument that had made the crossing detection definitive in a way that Voyager 1's crossing had not been. Voyager 2 carries a working plasma science experiment, an instrument that stopped working on Voyager 1 in 1980, long before that probe crossed the heliopause. The most compelling evidence of Voyager 2's exit from the heliosphere came from its onboard plasma science experiment. Until recently, the space surrounding Voyager 2 was filled predominantly with plasma flowing out from our Sun. The PLS aboard Voyager 2 observed a steep decline in the speed of the solar wind particles on November 5th. Since that date, the plasma instrument has observed no solar wind flow in the environment around Voyager 2. The solar wind that had blown continuously outward from the Sun for 11 billion miles simply stopped. On one side of the boundary, solar plasma. On the other side, none. The crossing was not ambiguous. It was a clean, dramatic, instrumentally confirmed transition from one physical environment to another, and the plasma instrument that Voyager 1 had lost before it could ever make this measurement captured every detail of it. The temperature at the boundary was the first number to stop the scientists analyzing the data. The spacecraft recorded the temperature between 30,000 and 50,000 Kelvin, much hotter than the local interstellar medium, probably because the plasma gets compressed as it hits the heliosphere. 50,000 Kelvin. The surface of the Sun is approximately 5,800 Kelvin. The plasma at the heliopause boundary, in the thin, low-density region where the solar wind meets the interstellar medium, was registering temperatures nearly 10 times hotter than the surface of the Sun itself. Not in terms of transferable heat, because the plasma is so thin that the energy it carries per unit volume is very low, but in terms of the velocity of individual particles, which is what temperature actually measures at the particle physics level. The particles at the heliopause boundary were moving extraordinarily fast. The boundary region was not a quiet interface. It was a zone of intense energetic compression where particles from the solar wind and the interstellar medium were being accelerated and heated in ways that produced temperatures an order of magnitude above what the models had assigned to that region. The magnetic field finding confirmed what Voyager 1 had found 6 years earlier and transformed it from an anomaly into a genuine scientific problem. An observation by Voyager 2's magnetic field instrument confirms a surprising result from Voyager 1. The magnetic field in the region just beyond the heliopause is parallel to the magnetic field inside the heliosphere. With Voyager 1, scientists had only one sample of these magnetic fields and could not say for sure whether the apparent alignment was characteristic of the entire exterior region or just a coincidence. Voyager 2's magnetometer observations confirm the Voyager 1 finding and indicate that the two fields align. Two spacecraft, crossing the boundary of the solar system at different locations 6 years apart, both finding the interstellar magnetic field pointing in the same direction as the solar magnetic field. The alignment is not a coincidence. It is a systematic property of the interaction between the Sun's magnetic domain and the galaxies at this boundary, and it was not predicted by the models built before either spacecraft crossed it. The physical implications require unpacking because they are genuinely strange. The Sun generates its own magnetic field through processes in its interior, and that field is carried outward through the heliosphere by the solar wind, filling the entire bubble of solar influence with a magnetic environment that is fundamentally a product of the Sun. The interstellar magnetic field is something completely different, generated by processes in the wider galaxy, the accumulated magnetic influence of stellar explosions, the organized motion of galactic gas, the large-scale magnetic architecture of the Milky Way. These two fields belong to completely separate physical systems. Where they meet at the heliopause, the expectation was a magnetic discontinuity, a clear change in field direction marking the transition from one domain to the other. What both Voyager spacecraft found instead was alignment. The field does not change direction at the boundary. It continues in the same orientation, from inside to outside. Something is coupling the Sun's magnetic domain to the galaxies at the heliopause in a way that leaves no magnetic signature of the transition. How that coupling works, why it produces the specific alignment observed, and what it implies for the physical relationship between the heliosphere and the surrounding interstellar medium are questions that the existing theoretical framework has not fully answered. The new papers confirm that Voyager 2 is not yet in undisturbed interstellar space. Like its twin, Voyager 1, Voyager 2 appears to be in a perturbed transitional region just beyond the heliosphere. This finding reframed what the heliopause actually is in a way that matters enormously for understanding the structure of the solar system's boundary. The textbook picture of the heliopause as a relatively sharp, clean boundary between the heliosphere and the interstellar medium, with undisturbed interstellar space beginning immediately on the other side, is wrong. What lies immediately beyond the heliopause is not undisturbed interstellar space. It is a transitional region, perturbed by the presence of the heliosphere itself, where the interstellar medium has been compressed, heated, and modified by the pressure of the solar bubble pushing against it from the inside. The extent of this transitional region, how far from the heliopause the interstellar medium returns to its unperturbed state, is something that neither Voyager spacecraft has yet traveled far enough to determine. The spacecraft are now in the interstellar region named the outer Helios Heath, where the interstellar plasma flow is significantly decelerated and heated by global compression and charge exchange processes. They are approaching the maxima in the plasma and neutral atom densities at about 200 to 250 astronomical units from the Sun. Voyager 1 and 2 have now reached heliocentric distances of approximately 172 and 143 astronomical units, respectively. The plasma density maximum predicted by the kinetic models, the point at which the interstellar medium is most compressed and heated by the heliosphere's influence, lies ahead of both spacecraft, not behind them. Neither Voyager is yet through the perturbed zone. Both are still traveling through a region that is interstellar in the sense that solar wind is absent, but that is not yet the undisturbed galaxy. The true interstellar medium, the material that has not been modified by the presence of our solar system, may be hundreds of astronomical units away. Neither spacecraft will reach it before their power gives out. The particle leakage finding added a dimension to the picture that the Voyager 1 data alone could not have provided. Solar particles, the charged particles produced by processes in and around the Sun, were detected streaming through the heliopause from the inside to the outside in Voyager 2's data. Voyager 1 had detected no such leakage at its crossing location. The heliopause is permeable in some places, and apparently not in others. The boundary does not have consistent properties around its entire extent. Where it is permeable, solar particles escape into the interstellar medium. Where it is not, they are contained. The variation in permeability from one location on the heliopause to another has implications for how the heliosphere protects the inner solar system from galactic cosmic rays, the high-energy particles that stream continuously through the interstellar medium, and that the heliosphere's magnetic field deflects and attenuates before they reach Earth. A heliopause that is variably permeable is a shield of variable effectiveness, and the degree of cosmic ray protection that the planets enjoy may fluctuate in ways that the models had not previously incorporated. The cosmic ray data from the crossing told a story consistent with both Voyager crossings, but slightly different in its details. When Voyager 2 crossed the heliopause, the flux of galactic cosmic rays, particles accelerated to high energies by supernova explosions and other violent events throughout the galaxy, increased sharply as the spacecraft passed from the protected interior of the heliosphere into the exposed interstellar environment. This was expected. The heliosphere's magnetic field deflects incoming cosmic rays, reducing the flux that reaches the interior of the bubble. Crossing to the outside removes that protection. What was slightly unexpected was the rate at which the cosmic ray flux stabilized after the crossing. It reached its new, higher level almost immediately, with very little transition period, suggesting that the heliopause is a more abrupt barrier to cosmic rays than to some other particle populations. The energetic particles from outside that the heliosphere had been blocking apparently responded to the boundary in a fundamentally different way than the solar particles trying to leak out through it. The 2025 scientific analysis of both Voyager spacecraft's data produced a new study examining shocks, compressible perturbations, and intermittency in the region. Both spacecraft are now traveling through using the combined dataset from both probes to characterize the physical properties of the outer heliosheath in ways that neither spacecraft's data could support alone. The study found evidence of shock waves propagating through the interstellar medium in this transitional region, pressure variations that suggest the boundary between the heliosphere and the interstellar medium is not static but dynamic, responding to changing solar activity and to the structure of the interstellar medium itself in ways that produce traveling disturbances in the plasma environment around the spacecraft. The interstellar medium, even in the transitional region just beyond the heliopause, is not a quiet, uniform medium. It is a physically active environment full of density variations, velocity gradients, and wave phenomena that the pre-crossing models had described in less detail than the data demands. Ed Stone, the physicist at Caltech, who served as the project scientist for Voyager for decades, framed the significance of what Voyager 2's crossing added to the scientific picture in terms that captured both the achievement and the open questions it produced. The Voyager probes are showing us how our Sun interacts with the stuff that fills most of the space between stars and the Milky Way galaxy. That interaction, the physical conversation between the solar bubble and the surrounding galaxy, turns out to be more complex, more dynamic, and more resistant to simple description than the models built from inside the heliosphere had managed to predict. The temperature wall at the boundary was unexpected. The magnetic field alignment was unexpected. The perturbed transitional region was unexpected. The variable permeability of the heliopause was unexpected. The consistent crossing distance despite opposite solar cycle conditions was unexpected. What the scientists receiving Voyager 2's data from beyond the edge of the solar system were confronting was the standard experience of science at the frontier. The models that predicted what would be found had been built with the best available knowledge and the best available physics. They had been refined over decades by some of the finest minds in heliospheric science. And the data from the boundary disagreed with them in specific, repeatable, instrumentally confirmed ways that required not the abandonment of the models, but their extension, their revision, their renegotiation, with the evidence that had just arrived from a place no instrument had ever been before. Voyager 2 is at 143 astronomical units from the Sun as of early 2026. Its plasma science instrument was shut down in October 2024 to preserve power, the same decision made for the same reason that Voyager 1's low-energy charged particle instrument was shut down in April 2026. The triage continues. The power continues to decline. The instruments continue to go dark one by one, each one a sacrifice made to keep the remaining ones alive a little longer, sending home a little more data from the transitional region between the heliosphere and the true interstellar medium that neither spacecraft has yet passed through. What Voyager 2 found when it shocked the world by crossing the edge of our solar system was not confirmation. It was complication. It was the discovery that the boundary is hotter than expected, magnetically aligned in ways not predicted, permeable in ways that vary by location, and surrounded by a transitional zone that extends further than the models anticipated. It was the confirmation that what Voyager 1 had found 6 years earlier at a different location and under different solar conditions was not a local anomaly. It was the demonstration that the edge of the solar system is genuinely stranger than the science built to describe it had managed to capture. And it was the beginning of a new scientific question, the question of what lies beyond the transitional zone, in the undisturbed interstellar medium that neither spacecraft has yet reached, that the data from both Voyagers will never fully answer, but will make sharper and more specific for every mission that eventually follows them into the dark.